Hello everyone and welcome back to Indian Genes. As we come to the end of 2020, this is our 15th episode, and thank you once again for all the support that we have been getting from you. Keep those suggestions coming in, both topics that need to be covered and guests that you would like to hear. Today we have a very special guest for you, a great achiever who has been involved with the Open University as a research assistant in astrophysics. This was when he started off in the field. He has also been a research student with the National Physical Laboratory. He has spent his time as well at the University of Toronto as a graduate teaching assistant. He taught 6 courses there, ranging from the first year Introduction to Physics to the final year graduation courses in Advanced Quantum Mechanics and Electromagnetism. As a PhD student at the Oxford University in London, he has been a team leader in a group of 6, advising the Oxford Climate Action Change Network on how to establish a collaboration between civic organizations in Oxford and the University of Oxford. He has worked on the robotic telescope based in Mallorca, Spain, called Pirate, to collect and analyze astronomical data on exoplanets. He has published several academic papers out there, including The Initial Conditions of the Universe, Screened Fifth Forces in Parity Breaking Correlation Functions, Pulsar Acceleration Shifts from the Nearby Supernova Explosion, and many more. He is currently working as a data scientist with ONI in Oxford, UK. We had a great conversation, and I'm sure each and every one of you listening to this episode is going to have a lot to take away from here, especially students that want to get into the field of astrophysics or have questions about the universe, the Big Bang, the beginning, and all the hard work that goes into being an astrophysician. So without taking more time, I now present to you my extremely enjoyable conversation with none other than Darsh Kodwani. Hello Dash, and it's an absolute pleasure to have you here on Indian Genes. Welcome to this podcast.
Thanks for taking the time, joking. It's my pleasure. So just a little bit about me. I was born in India. I was born in Ahmedabad in Gujarat, and then my parents moved to the UK. Actually, for the first time when I was quite young. I was 1, I think, and my dad moved to Manchester to do his PhD. That was the first time I came to the UK, and then we were here for 3 years. And then after he finished his PhD, he went back to India to take up a position, an academic position, in actually a small town in Gujarat called Adipur. So we were there for 8 years, and then my parents moved back to the UK permanently to where we are now, and I was 12 then. So since I've been 12, I've grown up in the UK, so I did the majority of my schooling here and also my university and higher education and so on. When I was in high school, I think I didn't really know what I wanted to do very much.
Like most of us.
Yeah, exactly. I was a very sort of, that's exactly how it was. But it was very late on. So here in the UK, we have the schooling system has 13 years, not 12 years, as we have in India. So when I was in year 13, or basically the end of year 12, we were learning physics. So I took, you can choose 3 or 4 subjects, and I took the sciences and mathematics during my end of my high school, which we call A-levels here. And I think I was always pretty good at maths, but I didn't know what I wanted to do with it. And when I started learning about physics in the end of my year 12 and the beginning of year 13, I really got interested into it. What really fascinated me about physics were things like when you first hear about quantum mechanics and particle physics. A lot of things you hear don't really make any sense, as I'm sure you would.
They still do. They still don't to me.
There's a lot of things don't still make much sense to me either. That's a bit of a fallacy that you start to understand things. I mean, you understand them how they work mathematically, but do we have a better intuition? I don't think anybody does about things like quantum mechanics. So when I first got introduced to these things, I got really hooked into physics. And then after that, it's just been what I've always enjoyed. And so I studied that at university for my undergrad, for my master's, and also for my PhD now.
Right. And if you could just take us back a little bit to before you went to the UK. So was
Hmm.
there anything that inspired you, or did you see yourself unconsciously getting drawn to that subject? Or do you think that you realized your interest in this much later?
The point you make was a very good one. Like, how, what is it? Perhaps there were things from my childhood. I think that's probably true because one thing my parents probably always did was read to me when I was a kid. They'd read to me, they tell me about all kinds of things about the world. And I think my nature has been always very curious, so I always liked learning about new things. So probably just asking basic questions and just getting the enjoyment of learning the answers to them is probably something that was ingrained in me from a child. And therefore, irrespective of subject, as I'll discuss, afterwards, even though physics is what I got into and what I've been educated in, I've diversified my interests even more. Even within physics, my interests are very broad. So I think in general, that's the attitude I have, and it's almost irrespective of subject, somewhat. It probably just happened to be that physics is the science that asks probably the most basic questions and the most fundamental questions about our world and the universe. So it's very easy to get into it, but as I've learned more and more, I've just got interested in more and more things as well.
Hmm. And you said you have a diverse interest in reading and getting to know more, or it's just the curious mind that you would want to know more. Uh, at,
Hmm.
at, at that particular time for you, I think you said it was at grade 13 or 13th year. Were
Hmm.
you at any time in the middle of any decision, should I go this way or that? Or were you very clear at that time that this is what I want to do?
Uh, I think after I got introduced to physics, it became fairly clear that I wanted to do physics. But as I said, this was very late on.
Hmm.
Prior to that, I really didn't know what I wanted to do. I thought I'd do some form of engineering because probably that's the only thing that I knew about very much.
Hmm.
Uh, and I knew I was going to be something mathematical because I've always liked doing mathematical things. But I think, yeah, once I got into physics and I read about, I learned it in school, and then I also read a lot of the popular textbooks, like the popular science books. So Hawking's books about the universe, and also Feynman's books I've found very, very enjoyable.
Hmm.
They're very engaging, and that I think after that it was clear to me that I wanted to do physics, and that remained so for many years.
Hmm. And do you remember, or do you have any one book that you think would have influenced you the most, or students that are listening to us right now would want to read that particular book? Is there anything that you would recommend?
That's a very good question. Feynman's book on the six easy pieces.
Hmm.
That's something that I really, really like, and I really enjoyed it. So I
Hmm.
think that's probably one of my favorite books in physics. But actually, it is not my. I read a lot, and so my favorite book by far is actually not a physics book at all. It's Thinking Fast and Slow, which is you probably heard of it. It's
Yep.
a behavioral economics book. It's not a this is not me giving some great wisdom. It's a very popular book,
Mm.
but I think that is a book that everybody should read. Anybody who likes thinking about intellectual things, because it really tells us about how our mind works. And I think that's, if anybody who is growing up wants to learn something, it should be more about being curious and being just having an open mind and asking basic questions. And these are the books that I think really do that, irrespective of subject.
Knowing that you were interested in physics is one thing, but then
Mhm.
having to actually get down and do the hard work day after day. Because from the outside, like you said, you could read Feynman, or you could read any of these books, and then you say, yes, okay, there is some calling. But let us know a little bit about what effort goes into to doing what you did.
Sure, sure. I mean, the short answer is a lot of effort.
Yeah.
Uh, Physics and maths are probably, maybe along with computer science, are probably the hardest fields one can take in undergraduate, at least in terms of how much work they entail, both in terms of studies and also sometimes the concepts can be tricky to understand.
Mm.
Um, so you know, I think once I set my mind on doing this, I still remember in my final year of school. That's when I actually really started studying properly. I didn't really study properly before then
Mm-hmm.
because I probably didn't know what I wanted to do. I just had to make sure that I could pursue the degree I wanted to, and so I spent predominantly that year just doing problems from my textbooks. I remember that very well. I did every single problem in my textbook, in my physics and math textbook, to the point that I'd even picked out the typos in them. Um, so it was a lot of work, but I think I really enjoyed it. The way I used to work was I just put some music on in the background, and I could just spend hours and hours doing it because I actually had fun.
Mm-hmm.
And I think that I was very fortunate that way because I found something that I enjoyed and I could also do. And I think when those two things are combined, then you can do well. So I'd just say that to anybody who wanted to do it, right? You should find something that you enjoy. I realize everybody says that. It's not always an easy thing to do. But if you find something you enjoy, it's really, really easy to, focus on it and work on it. And, to succeed in anything, I think you have to work hard. A lot of it just comes down to practicing. Lots and lots of practice. That's what it was.
Right.
But then, I think once you get to university, it was a bit different because because I was studying physics and not maths. There's a lot of concepts you have to understand, which is not about practice, which is really about sitting and thinking about it. So that then requires a different set of skills, which is focusing a lot. So sitting quietly and trying to focus is actually very hard. I think all of us will agree on that, particularly in today's age. And that's sort of a lot of what undergraduates in physics would have to do if you want to understand physics properly. And there's still things about physics that I don't properly understand. But to make an effort, you really have to sit and focus. That's what a lot of my undergraduate is about. And as I'll come to talk about research when I was doing my PhD, is almost entirely that. It requires a lot of just focused time working on problems.
Tell us a little bit about your research, how you got into it, and what were the areas that you were working on?
Mm-hmm. Sure. So I focused in a broad field of theoretical physics, which is different from experimental physics. In experimental physics, people will typically work on either building experiments, so that can be a lot of work in the lab, or out in a field, depending on what kind of experiments you're doing, and then you're doing a lot of data analysis of the experiments you do. So mine research is somewhat different. In theoretical physics, you're basically asking, you take the current models that you have to understand systems. Systems can be anything. And you ask the most basic questions about those systems and see where those models fail. That's, in a nutshell, probably what the best description of theoretical physics I have. These models are typically mathematical in nature. That's one of the things about physics, is that it seems that we can describe systems pretty well using mathematical equations. And so a lot of the time spent is trying to understand, analyze, and solve these equations. Not all of it can be done by hand. Often you have to use computers for it because the equations can be hard to solve. So a lot of time on a practical basis is gone in doing either solving equations on paper or just writing code to solve equations. So that's the area I've worked in. I can be even more specific.
Please go ahead.
Yeah, so the area that I have worked on mostly, I've worked on a couple of other things, but mostly it's been in theoretical astrophysics, which is trying to, that's again a very broad thing, so that encompasses things like the dynamics of stars, the dynamics of planets, the nature of galaxies, and the universe as a whole itself. And so I studied basically two things, two broad areas, one was trying to understand gravity, which is one of the four forces that we know exist in the universe, and what it's like in various situations on large scales, in very strong energy environments, such as in black holes. So I spent a lot of time studying that. And also the other topic that I work on, which probably I could say is my day job, was cosmology, which is studying the universe on large scales. So that means understanding the structure on very large scales, on the scales of many, many galaxies, and also what it was like at early times, how the universe starts, what are the things that are in the universe when it starts, how it evolves, and so on, as a whole. Not at small levels, but if you take the universe as a whole object, it turns out it's actually possible to describe the evolution and somewhat about how it starts. So that's what I studied. It's actually funny how I got into it, since you asked how I got into this area.
Yeah, please.
I was in undergrad. I was thinking about what I wanted to do for my postgraduate studies, so for my research. And I remember in my third year, my undergraduate was 4 years. In my third year, I was reading a lot about particle physics, a lot about string theory, and a lot about gravity. So I was thinking either I should go into studying gravity or particle physics. And I remember you had to choose, for our final year, we had to choose a topic that we were going to do a small research project on. I've been always very much independent, so I spoke to the person who I wanted to work with, who was a theoretical physicist, and then he basically gave me some ideas of things I could work on. And one of the things he suggested was more to do with gravity. And just around the same time, I was reading a book, which is called The Perfect Theory. I don't know if you've heard of it, Joachim.
Yeah.
It's a popular science book. Also physics. It's about general relativity.
Yeah, right.
And so I was reading that at the same time I was doing this project. And then by doing that, both sides, I was sort of on the popular side and also on the scientific side. I just really got into learning about gravity. And so that's the thing I pursued after that. And the funny story is, the author of the book, The Perfect Theory, is Pedro Ferreira, who's the person I ended up doing my PhD with.
Wow.
So that's an interesting story. Circle of life, eh?
Wow.
Circle, as people say.
You were studying particle physics, and then you were also studying cosmology. From the outside, from what that would mean to us, evolved into quantum physics, and you were also studying the macro world or planets around. That does seem to be one of the most open questions in physics today, if I'm not mistaken, and you also mentioned gravity. Is there some sense in the thought process what I'm putting across?
Yeah, it's definitely true. I'll just add one clarification, which is cosmology is typically not on scales of planets. So cosmology typically refers to things on the scales of galaxies and larger than galaxies, or the universe as a whole. So planetary dynamics is actually quite different. And I never worked in planetary dynamics myself.
Okay.
But yes, I worked on cosmology, so the universe on large scales and how it starts. That's in particular something that was the topic of one of the main topics of my research, is how the universe starts. And gravity, of course, comes into that. And then quantum mechanics is actually, I wrote a paper on something called Hawking radiation, which is black holes emit, and that is a very bizarre area in which you have to combine quantum mechanics somehow with gravity. So you're absolutely right that combining gravity and quantum mechanics has been one of physics' main goals for many years now. We don't have a particularly good understanding of how that's done. So perhaps before I do that, let me explain what the issue is. From what we know so far, we know there are 4 forces that people refer to in nature. Okay, in our universe, there are 4 things that can drive motion. A force is something that drives motion. One is called the electromagnetic force. That's probably the one that we are most familiar with, because that drives, electricity and the world we live in, basically. So that's electromagnetism. There is something called the strong nuclear force, which determines how nucleuses behave in atoms. And there's also the weak nuclear force, which is another force on the subatomic scale. Now, these 3 forces, we have descriptions for which rely on quantum mechanics. So quantum mechanics is a framework in which you can write down models of how the world works, which is actually different from what's known as classical mechanics. In classical mechanics, which is what we knew, from many years, from Newton on to basically the 20th century, till Einstein's days. Einstein played a big part in quantum mechanics, understanding quantum mechanics as well. So yes, classical mechanics was what was used to build theories up until quantum mechanics came around in the early 20th century. And so those two frameworks, classical and quantum, are fundamentally different. Classical mechanics allows you to write down models that describe systems deterministically, which means you can predict exactly what would happen at a later time if you have the configuration of the system at a given time. Okay, so if I have a system and I know all of its parameters right now, then I can describe with perfect certainty what will happen in 10 years' time, in principle. Might be too difficult to do that, but in principle, there is a way to do that. That's classical mechanics. Quantum mechanics is very different. It doesn't allow you to do that. It is probabilistic in nature, which is actually quite difficult to grasp because it says fundamentally there is a limit to how much you know. There are things you can describe that will probably happen, but you can never know for certain what will happen. So that's the distinction, and it's a very fundamental distinction between classical and quantum mechanics. So coming back to the point of gravity and quantum mechanics, so as I was saying, we have the four fundamental forces: we have electromagnetism, weak nuclear force, and strong nuclear force. And these three theories we have descriptions of. So we have mathematical equations that describe these theories in a quantum mechanical framework. Okay, and we observe that the universe, the particles in the universe, obey quantum mechanical rules and at the small scales. However, there is a fourth force, which is gravity, which dominates the dynamics of motion, the dynamics of things on very large scales, such as planets and so on. We're all very familiar with gravity. However, we don't have a set of equations that can describe gravity that are quantum mechanical in nature. They are still based in the classical realm that we've had since Newton, and so it's been a target for physicists to figure out a set of equations that are quantum mechanical for gravity for many years, for over 50 years. But we haven't. There isn't an accepted theory. There was a very strong attempt at it using which was developed in the, I think, starting probably in the 70s, but really caught on in the 90s, which was string theory, which was an attempt to do that. However, even that nowadays, I'm not an expert in string theory, but the people who are experts in string theory, I think, working on it as a pure endeavor for unifying quantum mechanics and gravity has sort of had its time now. People don't work on string theory very much either because of, as far as I understand, the mathematical difficulties in actually pursuing it, and also the lack of predictability you get from string theory. It doesn't actually predict a theory that can describe the world in a very distinct way. It just allows many possibilities, which makes it hard to test.
Is it also because of the additional dimensions that come into it?
That is, I don't think that's the case. So if I elaborate, string theory is typically written down in 11 dimensions. So the idea there is that in string theory is that in addition to the dimensions we have in our universe, which is actually 4, it's not 3. So there are 3 spatial dimensions that we see, in our daily experience. And then Einstein taught us, in actually the special theory of relativity, is that you can think of time as an additional dimension. And so space and time form a 4-dimensional object, which we call space-time. And that object has physical properties. It's actually something real. And that's the idea of relativity, special and general relativity. That's what Einstein is probably most famous for. So that's the canonical view of physics. However, if you have something like string theory, the idea there is you have, in addition to 4 dimensions, you have 7 more dimensions, which are very small, and therefore you don't see them. But as far as I understand, that is not the problem with string theory. The problem is that it is a theory. So you need to take the 11-dimensional world that string theory allows you, and you have to somehow get to the 4-dimensional world that we live in, right? It emerges on some scale. At some scale, we have to look like the universe looks today, right?
Right.
And as far as I understand, the transition from going from 11 to 4 dimensions is not unique, and it's not just the dimensions. It's more like the properties of the forces that we have. You know, the electromagnetism, the strong nuclear force, the weak nuclear force, having the properties that they have, and the strength that they have. There's no unique way of doing that in string theory. There's no unique representation of those, which means it's very hard to predict the kind of universe you'd see today. At least it's mathematically very intractable to do that, and therefore, you know, if you can't predict what's going to happen in a theory, it loses an appeal, right? I mean, what are you going to do with a theory?
Right.
So as far as I understand, that's sort of what's happened with string theory, and even the sort of most famous string theorists who have worked on this don't work on it anymore. There have been schools that have come from string theory, which are things like holography, which I can describe briefly later if you wish. But those things can be thought of as almost separate, even though they were inspired by it. So that's sort of the state of string theory, and I don't think we have a great understanding at the moment of any alternative theory either.
You have spent a lot of time with the Big Bang model and the evolution formed there. I think it would benefit if we could talk about that and then move ourselves through a little bit of an easier explanation, because we do have a lot of explanations out there. All of this has given us a clearer picture of what happened from the Big Bang. So why don't you take it from there?
Sure. So what I'll do is I'll take an approach in which I'll actually describe what we think about when we say the Big Bang. Okay. So the Big Bang model, and I say model because what a scientist, what a cosmologist or a physicist would typically mean by the Big Bang is it's a model that we have that describes how the universe evolves, but it doesn't describe like a moment where it starts. Okay, there isn't a description of how it starts, of where, like, what is that moment. We just have a specific time up until which we understand how the universe evolves. If that makes sense. So the universe today is something like 13.9 billion years old. So you may ask, well, that means there was a time at which it was 0 years old, right? And isn't that what you would call the Big Bang? And yes, that probably is something that you may call the Big Bang. The problem is we don't have a description of what the universe looks like at time equals 0. What we have is a description of how the universe looks at very early times. So that can be types, depending on, you know, which model you believe, which I'll get into. There is an addendum to the standard Big Bang model, which I'll describe, known as inflation, which if you believe, then you can understand the universe at much earlier times as well. But for the moment, let me just describe what the standard Big Bang model is. Okay, so in the standard Big Bang model, the universe starts in a phase where it's just filled with light. Okay, it has particles of light, which we call photons, and it has a bunch of other particles, but they're also very hot, and therefore they all behave like light. The problems they have, by light I mean anything that's moving at the speed of light, and if you have any particle and you heat it sufficiently, it can get very close to the speed of light. So the universe is a phase when the whole universe, you know, think of the whole universe, is very hot. So it's very.
And what is? How would you describe the size here? How small are we talking?
Oh, that it can be. You know, it'll be like it'll be far smaller than even, you know, atomic scales. So I'm talking about times where you know, if today, as I say, is 13 billion years since that time.
Mm.
Times I'm talking about are when the universe is, let's say, less than a second old.
Okay.
So that's how early we're talking,
Okay.
and it's extremely hot as well. So the universe is very young. It's very hot. By hot, I mean of the order of 10 billion or 100 billion Kelvin or Celsius.
Mm.
Just think about that temperature. The entire universe is
Wow.
like that.
Wow.
Up until that point, we can describe what are the properties of the universe. Okay,
Mm.
and at that point, as I say, it has a set of particles in it, which I'm not going to describe in detail. But as I say, the main property they have are that they are hot, and therefore they behave a lot like light. And this phase of the universe, where everything is really hot and things are dominated by light, is what we call radiation domination.
Mm-hmm.
Okay, radiation dominated phase of the universe. And in this phase, there are certain properties about how the universe expands, about how the temperature changes in the universe, that we can describe very well. Okay, so that's the standard. In the standard Big Bang picture, we know the universe starts at some time, which, as I say, it can be anything up to 1 second after the Big Bang to realistically, up until something like 10 to the minus 6 or 10 to the minus 12. So 10 to the minus 6 means 0.0000001 seconds. So that's up until we actually have a fairly good understanding, I would say, of how the universe behaves. So there are very rigorous equations that I spent a long time studying, actually, that describe how the universe behaves and how it evolves up until that time. And the other thing that the universe has is that it's expanding. Okay, so what we know is that the universe was behaving like radiation, was dominated by radiation, and it was expanding at that time.
Mm-hmm.
Okay, and from that initial state of a hot, really dense phase with radiation, and it was expanding, we can describe what it looks like up until today.
Mm-hmm.
Okay.
Wow.
And that journey of description from how it goes from every phase onwards from the radiation dominated phase is what we call the Big Bang model.
Mm-hmm.
Now, of course, we've tried to extend our knowledge even beyond the early times that I told you, right? About 10 to the minus 6 or 10 to the minus 10, depending on, how you think about the early universe. There are models which allow us to extend our understanding beyond the so-called radiation-dominated phase of the universe.
Mm-hmm.
And the most popular one is called inflation. What inflation is it's a phase in the stage of the universe where it is before radiation domination. And the inflationary models will typically start at times much, much shorter. So they would start at times of order, 10 to the minus 35 seconds or 10 to the minus 32 seconds after the Big Bang. Okay, so until that time, what I'm saying is we have a description of how the universe evolves from that time.
Mm-hmm.
So those numbers are quite amazing when you think about, how could we understand what the universe was like at that time?
Absolutely.
But I'll describe, after I do this description, I'll also describe how we know these things. Okay, I'm telling you things, then I'll tell you how we actually know this. So during inflation, the idea is that the space-time itself, so our universe itself, expands very rapidly. Okay, it expands by, again, in the same scientific notation, 10 to the 26 times its size, roughly, in a fraction of a second, in sort of a time scale of 10 to the minus 32 seconds. So that's a ridiculously quick expansion of the universe. In fact, if you think about it, that's actually an expansion of the universe which is faster than the speed of light.
Wow.
And of course, you may ask, how do things expand faster than the speed of light? Because that's probably one thing most people do know about physics, right? Is that things don't travel faster than the speed of light. But that is, just to clarify, things cannot travel faster than the speed of light within the universe, but we're talking about the whole universe expanding. Okay.
Yeah.
Does that make sense? Those are two different
Yeah.
things. So
Yeah. So there is nothing for. There is nothing it's expanding into, but it's expanding and creating at the same time. So.
Yep. Good. We don't know if it's expanding into something, but we just know it's expanding. Good. So that's the idea of inflation. Now, the way this comes about, the way we know these things are from observations we do of the sky, right? Actually, everything we know about the universe is actually not everything. The things I'm telling you, we know about from looking into the sky. A lot of the other things that we know about the particles and the forces come from accelerators, from particle accelerators, which try to understand the basic forces in a laboratory situation. But the universe itself, you have to look out and observe to know what it's like on large scales. So the key piece of observation that tells us about what the universe is like and how it evolves is known as the cosmic microwave background radiation. Okay, let me explain what that is. So if you go outside and you point a satellite dish that can measure microwaves into the sky, in every direction you'll get a signal. Okay, you can do this. What that signal is at a particular frequency is the light that is left over from when the universe starts to cool down enough from this hot phase. So let me explain why that would happen. If you think of the universe as a whole at early times, when it's really hot and really small, what happens is that the light itself that's in the universe, as I was saying, it's dominated by light, cannot travel very far. It's like being in a foggy place. If you're driving through fog, we all know you don't see too far into the distance, right? That's because light will then bounce around in the fog and get stuck there. It doesn't travel. And that's known as opacity, right? I think that's something we're all probably familiar with. Is being opaque to more or lesser of an extent. So the universe, when it's very hot, is actually opaque. Light doesn't travel very far. But as it expands, and this is the key thing about its expansion, it cools. So if you take a box of light or radiation and you expand it, it'll cool, and that's what the universe is basically at early times. And as it cools down, there comes a point at which light suddenly becomes transparent. So the universe becomes transparent to light. So light can travel long distances. Okay, that happens roughly around 380,000 years after the Big Bang.
So till about 380 years, 80,000 years after the Big Bang, once the universe started cooling, this light could then travel with the expansion.
That is a great question. Light is traveling within the space, but the space itself can still be expanding faster than light.
Okay.
Yeah, that's a great distinction. Yes, thanks for pointing that out.
Okay.
Light will continue to travel within the space, but the space will still expand. It can still expand faster than light.
So that means if we get to that point of when it started expanding, or when light started traveling, there's no way we could see past that, right? Because it was opaque. We'll never know the initial moments.
Correct. The light cannot go beyond. You cannot get light from beyond that time.
Wow.
380,000 years.
That's so interesting.
That is very interesting. However, here's something more interesting.
Yeah.
There are other particles which do not interact with light, which are called neutrinos. Okay? Those particles actually do travel to us. So in the same way that the universe is opaque to light, it's also opaque to neutrinos at earlier times. They only interact via the weak force, which is the other force that I mentioned. And you can actually see up until approximately, I think, a couple of seconds after the Big Bang. So
Whoa.
you can see neutrinos in principle. In principle, we haven't detected those types of neutrinos. Once they are, like, as I say, a couple of seconds after the Big Bang. That's a big difference, right? Because the other one is 380,000 years. The first one is a couple of seconds. So if you can detect, and that's known as the cosmic neutrino background, that's often spoken about. But if you can detect that, and there are efforts to try and think about how you detect that and what you can learn from it, because that would of course be a probe into an earlier phase of the universe. But that's the amazing thing, is that we have so much confidence in our model that we can, even though we can't see beyond this phase of light, we call this phase recombination. I'm just going to say that so I don't have to keep saying the same thing. The point where light, the universe becomes transparent to light, and we see the cosmic microwave background, or the CMB, is called recombination. So even though we can't see beyond recombination, which is 380,000 years roughly, we have such good confidence that we know and we expect that there would be neutrinos even before then, that we should be able to detect.
And
that,
sorry,
yes.
So I just want to stick on to this 380,000 years a little bit more. The four forces that you started talking about, when do they come into the picture? Are they somewhere part of this expansion? Are they within it? How are they divided?
Good. So all the four forces. So gravity, of course, gravity is somewhat different because it describes how the universe itself is expanding. So it has this inherent expansion within it. The other forces, we actually need to write down the description of how the particles and how the particles evolve and interact before. So the fact that, as I was saying, you have this phase where neutrinos exist, and we know that they should become transparent at roughly 2 seconds. To understand that, we need to have this description of the other forces. They come into play. Even before that, I said neutrino decoupling. Even before that, there are phases, something known as the electroweak phase transition, which I won't describe in detail. But things like that require the description of all of the other forces. And if you go further back in the very early phases, this is probably the limit of what we understand. If you don't include inflation, there is a phase where the universe is just filled with what's known as quarks and gluons, fundamental particles. And these are very closely related to the strong nuclear force. So all of the forces come into play, and all of them have a description. And our model is good enough that we have a lot of confidence that these things exist, and we have observations that tell us about how they interact, what is the strength of these forces, and so on. There is perhaps one more observation I should mention that actually gives us a good insight, which I haven't mentioned, which is not the CMB, which is known as something called, the event itself is known as Big Bang Nucleosynthesis. What that means is the description we have of the other two fundamental forces, electroweak, the weak force and the strong nuclear force, they will determine the quantity of different nuclei that form, or different atoms that form, so in the universe. So the amount of hydrogen there is in the universe, or the amount of helium there is, or deuterium or lithium, you can actually calculate how much that should be at early times in the universe, if you can make assumptions about the other forces. And then you can, of course, go out and measure. I'm saying these things as if they're very easy. They're actually quite difficult to measure and estimate. But in principle, they allow you to probe your model of the early universe, because if the different forces behaved in different ways, you would have a different abundance of hydrogen and helium in the universe than what it would be today. And so by measuring it, you can narrow down the models of what the different forces are at the early times.
That's a time when all these quantum fluctuations would have been happening with all the particles that you just spoke about.
No. The quantum fluctuations are different. There are always quantum fluctuations, but this is not a phase where quantum fluctuations are important, so to speak. the quantum fluctuations, actually, this is actually one of the strengths of inflation. It's really in the context of inflation that quantum fluctuations become very interesting. Because the idea behind inflation is that it's driven at such an early time that you would have a lot of quantum fluctuations. And then the quantum fluctuations are in the densities of the particles, for instance. So at different locations in the universe, you'll see different densities of the particles. And therefore, when things grow, when the universe expands and things collapse in on themselves under gravity, you would form structures. So initially small structures, but as the universe gets old, structures as big as galaxies. So the idea behind inflation, this is why it's really popular, is that it can allow you to take a very natural mechanism, which is quantum fluctuations, which we know exist, and turn them into large structures that we see today. So it's actually an attempt at explaining where the structures we see in the universe comes from, where the galaxies, where do these things. So it's a very, very nice idea because it allows you to take quantum fluctuations and turn them into the structures you see today. But I should say, there are many different types of there are many different models of inflation. They all have slightly different predictions. So inflation is also a little bit not as extreme as string theory, but it's a little bit like string theory because it's actually very hard to define what it predicts often. And as I say, if you have a theory that loses its predictive power, then it often becomes less useful. But when it's not as extreme as inflation, but there are certain problems that are quite problematic, in my opinion. Different people have different views on that one.
The first 3 minutes were a very, very active time, active one, but the first 3 minutes were extremely important because everything else that we see after 3 minutes kind of was defined in that very first moment, right?
Yeah, so the thing, it's actually even more extreme. Inflation goes from, as I say, like 10 to the minus 34, 32 seconds to a few minutes.
Wow.
That's when inflation happens. The first 3 minutes is actually a reference to Big Bang Nucleosynthesis, BBN, the thing I just told you about.
Right.
That happens at roughly 3 minutes after the Big Bang. So there's a popular book by Steven Weinberg which describes basically a lot of physics that happens up until 3 minutes, in the first 3 minutes, and that's how it's got really popular. But it's a description of how exactly what we said, that inflation has the ability to take quantum fluctuations and imprint them into structures, and also then how that affects the abundance of different types of atoms, so hydrogen, helium, and so on. That's the yes.
Go ahead.
No, I was going to say that's basically the whole description of 3 minutes is how that happens. Okay. And this is actually, brings me on to a different, slightly tangential point, perhaps, which is the early universe is very nice for studying physics because it brings together all of these different aspects. It brings together quantum mechanics. It brings together different forces. It brings together thermodynamics. You have to take into account all of these things and put them into some coherent picture that allows you to describe the universe in phases where you don't see it. And that's sort of, the first 3 minutes is a good example because, as I say, you don't see light, at least before then. The best you could do is perhaps see neutrinos, but that hasn't been detected to any great significance. So even though we don't see it, we have such a good understanding of our physics that we can confidently say that we can describe the first 3 minutes, even though we don't see it. Yeah. The best first picture we have is, as I say, 380,000 years after the Big Bang.
And when we say 3 minutes, that's 3 minutes for us now in hindsight with time having evolved as one particular dimension. But when all this was happening, would that 3 minutes be relevant? Because I don't know how does time fit into this first 3 minutes at all when there was only 3 minutes?
So you're asking that question, I assume, in the kind of relativistic context. Correct. Like is time being stretched or something. That does happen, but in this situation, that is not taking effect. It is, it'll be 3 minutes, roughly three. I say it's not exactly 3 minutes, but roughly a few minutes as we measure today. Yeah. There isn't the notion of sort of time changing its length or anything at this point.
Right. This particular initial moment seems to be quite amazing.
For sure, for sure. As I say, we don't even have a description of that moment, right? We only can describe what happens a certain time after that moment. But it is amazing, as you say, and it's worth just sitting on it and pondering it for a moment, that you can understand the universe. If you believe it, if we think something like inflation happened up to 10 to the minus 32 seconds after the Big Bang, which is a ridiculously small number, even though we don't see it. Even though we have no probe of that, no direct probe of that. We only have inferences based on that. That is, I think that's probably one of the most amazing things about modern science, is that we can describe something, probably one of the most fundamental things, which is what is the universe, where does it come from, how does it start, to this level of precision, is quite amazing. And it's a lot of fun to be a part of that journey.
Right, and the inflation model, is that now the accepted norm in science, or is there any other research or anything that you think needs to be looked into as an alternate model?
So that, of course, I can give my personal answer. I think inflation, it's a beautiful idea, just based on the theoretical understandings that it allows us to have, and also most of the inflation models are fairly simple, and that's one thing we like to do in physics in particular. You like to look for the simplest models that you can use to describe a system, right? That's something that's probably not often appreciated, is that for any given system, there are probably different ways of writing down models to describe it, but the models that you think are useful are the ones that are simplest. When we write down the models that describe the early universe, and we try to do inferences based on those, one of the things that we do is, even in a statistical sense, when you look at, you have to understand these things statistically. Even in a statistical sense, we prefer models that have that are simpler. By that I mean they have fewer parameters, they have fewer things in them. So the simpler the model, usually we think the better it is. So inflation has that going for it in many things. But as I say, there are many models of inflation. There isn't one model. It's more of a framework for writing down models. So I think it has certain issues that I mentioned briefly, which are to do with how it makes predictions about various things, about various properties. It's known as the measure problem, which basically comes down to the fact that it's not immediately clear how you define probabilities. And when you don't know how to do that, it's not clear what the predictions even mean. So that's been a problem that's been around basically since inflation was first postulated. So it has certain problems. Now, the question then is there, regardless of the theoretical understanding of it, do our observations say definitively that inflation happened? Observations can prefer certain types of inflation models. That is true. Do we have a really good alternative to it? I don't think so. There are things, things actually, the research that I did on this area, I was focusing more on models that weren't based in inflation. I was much more agnostic to how the universe actually starts, and just looking at going much more based on the observations. So based on what we know, based on what we see in the CMB, what are the possible ways the universe could start? That's something that I attempted to answer, or at least ask. And in that case, there are different properties of the universe that, in principle, should be allowed, that in inflation probably wouldn't be allowed. These are to do with, it's going to get a little bit technical now, but I'll try my best. So when you have this early phase where the universe is filled with particles and radiation, the different, there's all of these particles and radiation will have perturbations in them. By perturbations, I mean some parts of some of the particles will have more density than other particles. Now, the way these perturbations, as I call them, these differences in the energy densities evolve, that is something that we observe. Okay. Now, depending on how the universe starts, will of course determine what you observe. Now, if you assume inflation happened, what often happens is some of the perturbations that you can have wouldn't be there. So they are often not even written down, even though they, in principle, could have an observable effect. So I spent a large portion of my time looking for these different type of perturbations that, in principle, wouldn't be there in inflation. Now, if you could go out and see them, then that would be a bit of a problem for inflation, because most models of inflation, you shouldn't have those types of perturbations. So that doesn't give you an alternate model to inflation, but it does give you a way of testing it, if you see what I mean. There are, as I say, other models of inflation, such as there are often postulated theories in which the universe actually doesn't start off at a given point, but it's been around forever, and the universe goes through cycles. So it expands and then it contracts, and then it expands and it contracts. That's an alternative to inflation, but it's less well established, and it has somewhat of a similar predictive power to inflation, but it's somewhat more contrived, in my opinion. So, on a theoretical basis, I think inflation is probably okay, even though it has these issues about predicting, or like how you make sense of probabilities, just because I feel like, at least as far as I know, there isn't a very good alternative to it. But observational front, like what does it actually predict and what you measure, I feel that there is still work to be done for it to be really considered, as the definitive explanation of how the universe starts.
And it's so interesting because obviously for what you do in the field that you do, in the science that you do, you're studying the Big Bang and you're studying the inflation model. But for a lot of us, what happened before the Big Bang? So I'm sure you've heard it a lot of times, but from a theoretical point of view, you can think about a lot of things, but how do you answer that question?
Well, I don't think there is an answer to that question.
Right, exactly.
We don't even have a description of what happens at the bang, so to speak, at the Big Bang, right? As I say, everything I've been describing has been descriptions of what happens after the bang, right? Inflation is something that would have happened 10 to the minus 32 seconds after the bang.
Exactly.
The radiation-dominated standard Big Bang picture that I mentioned would have happened, let's say 10 to the minus 10 seconds after the bang, right?
And would we ever get to that stage where we would get closer to the bang, or study times closer to the bang itself?
Sure. The honest answer is I don't know, but there is a limit. Well, there is a quantum limit, basically, to go beyond which we would need to have probably a description of how gravity behaves quantum mechanically, which is known as the Planck era. So there's this scale in quantum mechanics of when quantum mechanics becomes important, which is known as the Planck Scale.
The shortest, that's the shortest distance, or shortest scale, right?
Correct. That's like the shortest distance beyond which, it's like the units in which everything comes. It's called the Planck unit. So there's basically a Planck scale beyond which we would have a very difficult time understanding what's happening, given the current knowledge of physics. And the Planck time is 10 to the minus 43 seconds.
Okay.
So understanding the universe before 10 to the minus 43 seconds, just think about how small that number is to begin with, would be hard. Would be very hard.
Very hard. And was that one of the reasons string theory did at one time seem very interesting, because of the additional dimensions that if you can't go past the Planck scale, then you have to go in some other dimension, right?
But I'm pretty sure that the Planck scale is still the fundamental limit, even in string theory.
Okay.
In any dimension, as far as I know, but I might be wrong on that. But I think that the reason string theory was popular is because it had this potential of describing gravity in a quantum mechanical framework. And if you can do that, then you can, of course, go beyond this Planck scale and actually have a description at that scale. But as I say, because there's lack of predictive power, it's sort of lost track. But that doesn't mean it's not a nice theory.
Right.
I think a lot of string theorists today, actually, string theorists work in mathematics departments as opposed to physics departments now, because it's a very interesting area of mathematics. In fact, one of the main developers of string theory, Ed Witten, he won the Fields Medal of Mathematics.
Yeah.
He's a brilliant mathematician. So it's a very interesting endeavor still. It's just not clear if that is the description of our universe.
And your understanding would be, you've beautifully explained all this to us. And your understanding would be, do we now continue to expand? And we've spoken about the Big Bang. If we had to get to the other end of it, what do you think? What is your current understanding, or what is the understanding in science? How is it going to end?
So at the moment, we have discovered in the last 25 years, that the universe is not only expanding, but it's also accelerating in its expansion. So it's actually much like the inflation period at early times. So in the inflation period I mentioned, you have this really quick expansion of the universe in which the expansion accelerates. Actually, that's the definition of an inflationary epoch, is that the universe's expansion is accelerating. Okay. Now, we have discovered, as I say, that currently the universe is also doing that. So there was a phase, if inflation happened, that happened early times, and then it stopped, and the universe expanded, not in an accelerating rate, but we've now discovered that now the universe is also expanding at an accelerated rate. So that is a puzzling fact, because if you look at just the universe in the presence of gravity, then our expectation would be that the universe should not accelerate in its expansion. It should slow down in its expansion, because gravity should slow it down. It should pull it in some sense. So this is a very puzzling thing. Nobody expected this. And this comes under the name of something we call dark energy, or cosmological constant, which is, it's not an explanation. It's just the name we give to this phenomena that the universe is accelerating. We don't have a great, there are some models of what it is, but nothing that is in any way conclusive. A lot of the efforts now in cosmology have gone towards actually just pinning down the nature of this expansion. Like, is it static? Of this acceleration, like, is this acceleration changing? How is the dark energy going to evolve with time, and so on? So to answer the question of what happens going forward, it really depends on the evolution of this dark energy. Like, is it something that is just a fixed number? Is it something that's always going to be there? In which case, what's going to happen is the universe will continue to expand at an accelerated rate. And if you just extrapolate into the far, far future, then what's going to happen is everything will just get pulled apart. Even the atoms themselves will get pulled apart, until you reach a phase where, there is nothing in the universe except from just the fundamental particles that are just sitting around. That would be what would happen if the dark energy that we observe today remains as it is and it doesn't change with time.
And that means gravity would not really have any impact anymore?
Gravity, well, that's a great point. Gravity will have an impact for objects that are within its reach. So what that means is there are two things happening, right? One is the universe itself is expanding, and it's expanding quicker and quicker and quicker. The other thing is that gravity will pull matter into it, right? Into itself. So gravity is attractive. So perhaps a good analogy would be something like, if you look at a drain in a sink, right? If you have a sink, you fill it with water, and you have a drain. Now, you can think of perhaps the water moving outwards. So imagine somehow the water is moving outwards with some flow, and the drain is trying to pull it in. So the water moving outwards is the thing that you can think of as dark energy, and the drain pulling in is the thing you can think of as gravity. Now, there comes a point at which if the water moves quickly enough, right, it's going to escape the pull of the sink, and it's just going to continue to expand further and further away. But if the sink is strong enough, then it'll pull it in. And so if the universe expansion is accelerating, what that means is that the water in this analogy is accelerating, which means it's going to keep moving faster and faster and faster. So at some point, gravity will just not be able to hold things together.
That's very interesting.
Yeah, that would be the extrapolation that one would make based on the current observations of what we call dark energy. Yeah.
And if there's so much of action that happened in the first 3 minutes, what are the chances of whatever we talk about the future not happening in 3 minutes? In the sense of, if it all started and excitingly inflation and everything took 3 minutes, what I'm getting at is the end could be 3 minutes.
I see what you're saying. The inflation was even much shorter than that.
Yeah.
But I know what you're saying. You're saying, is it possible that it'll just end very dramatically in the sense that
the way it started?
And you're right, because if something is, it's exponential expansion, right? If the universe expands exponentially, or if anything happens exponentially, right? It's this weird thing, right? If let's say if something is doubling in size, right? And it doubles in size, let's say, in 1 second, then in 4 seconds it's doubled 16 times, right? So it could be that. So it could very well be what you're saying is that the universe would expand if it's doubling, for instance. This is just an example, right?
Yeah.
It's doubling, then in a few seconds, it's going to double so much that everything will be ripped apart. That's possible. It'll reach there'll be some point beyond which gravity can no longer hold together atoms, and you'll cross that sort of in a second or something.
And Dash, what are the questions currently that keep you awake? In the sense, what are you really excited about, or what is something in science or something in the field that you are studying that you've not yet got to grips with, or you still think that there's area for it to be explored a little bit more? Because I'm sure people listening to us or students listening to us here would find that interesting and may even venture into those areas.
Sure, and I said, that's, I think, the part of why we're doing this, right, is to inform people, and hopefully, they can come solve a lot of these problems.
Yeah.
So, that's a great question. There are probably, various things, but one thing that I've been thinking about and have been meaning to try and work on, which I haven't got around to yet, is in the very early times of the universe, as I say, if you just look at the universe agnostically and don't assume something like inflation happens, you can still ask basic questions about how the universe starts. In particular, one thing that actually you mentioned, which was, can you describe the origin of structure in the universe using quantum fluctuations? So I've been thinking about, is there a way in which you can test that, or have more general models that allow you to look for the quantum nature of the early universe? Okay. I think that's a very general, broad topic, but I think that is a very, very interesting area. And so one thing that I've always found really, really puzzling is to do with, it's in quantum mechanics, is known as quantum entanglement. Okay. What quantum entanglement is, it's basically, without describing in too much detail, it's a way of interacting between particles that otherwise should not be able to interact with each other because they would be too far away, or there's no way for them to communicate with each other. But through quantum entanglement, it seems to be that can happen. And quantum entanglement is probably the most quantum thing about quantum mechanics.
Yeah. And is it also the quantum computer? Are they trying to work on the same on exactly quantum entanglement and information being passed on? Is that the same field?
Yes, that is. Yeah, I mean, absolutely. Quantum information, quantum computing, these are all very, very closely related to entanglement. And so, I mean, this is a controversial statement, but I think anything that is really quantum has to do with entanglement, and anything that isn't, it doesn't. But I mean, there might be exceptions to that. But entanglement, I find, is a really interesting and puzzling thing. So I worked on this in the context of black holes and Hawking radiation that I mentioned before. But I've been thinking about ways to basically, in general, calculate how much entanglement there is in the early universe, by making some very basic assumptions about how the structure should form in the universe. And that is it's a very speculative area. There are a few people who work on it, but I think that is something that I find really, really interesting, because if you measure that, if there is a way you can detect that or calculate that that should happen, then that is, for me, the telltale sign that the universe starts in a quantum state. Otherwise, it's, it in some sense it must, because we have no reason to believe that as you go at earlier and earlier times the rules of physics should change. I don't think, but I think answering that question would be really amazing, is to look at how quantum the early universe is. That's something that
I'm sure a lot of kids would be asking that question, but coming back to that question again. So, what would you, if you were talking to parents with kids, let's say 8th to 10th grade at the moment? I'll start with 8th to 10th grade first. Is it that difficult for us to find the right place for our kids to go and further this particular line of education, or what is the path that you think kids here, for example, in India, or parents who think that their kids are interested in this field, but may not know exactly, what do I do next? Or we just follow the pattern of getting to college and then finding a university. Is this something that you have thought about, or you could help us with?
I think I'll answer two things. I'll give two answers to that. One is, in general, what I think is a good thing to do for anybody growing up, which is just to have an open mind and be curious. Okay, I think if we can just inspire that into people, I think that is the most important thing by far, like irrespective of subject, or just convey the fact that being curious and asking interesting questions and basic questions is really important and is really fun. Okay, I think that's the best thing I feel like one can do, because I think a lot of there's often people misunderstand what science even means, and science to me at least means it's just a method of thinking. It's like a frame of mind, right? It's about being critical and being able to think rationally through basic observations that you make about the world, right? Now, that doesn't have to be a discipline in and of itself. It can be anything. How you interpret what you see on the news, how you interpret something you read, how you approach homework or anything in school. If you have this sort of mindset of just thinking through things rationally and just looking at what you really know, I think that is probably the mindset that I think is the most important thing to have, irrespective of subject. And I think that is one thing that we should all focus on. And then I can come back to your question about if you want to get into physics, how do you do that, and so on, right? Well, I think physics, and in particular theoretical physics, is very mathematical in nature. And I actually didn't really find the high schooling in physics very useful, for me at least. It was very interesting. I think that was the key thing. It intrigued me, and therefore I was hooked into it. But what I learned in high school physics wasn't particularly important. I think when you're in high school, and to some extent in undergraduate, the key thing to do is to have a very good mathematical background, to be good at maths. That is, I think, very important, and that goes beyond physics. If you're good at maths, you can work in a variety of fields, so that's good. The other thing that's becoming increasingly important is to learn how to program, because the problems that we have today have become such in physics or in any field that you need to be able to program things to solve equations or to analyze data or to make sense of it and so on. So these are the two skills that I think are really, really important to learn in high school. And the good thing is, if you're good at maths and you're good at programming, then you're a very valuable person, because you can work in any number of things. These two can take you in any field, almost any field. So I think that's the advice I would give to people in high school, that's if of course they're interested in this, right? I mean, if you want to do art, that's an equally fun thing to do, and you just do that. But if you wanted to do the sciences, and particularly the mathematical sciences, be good at maths and programming, and then I think the doors are open. And I don't think you need to. I don't think there's anything in particular that that is lacking in our schools, at least in India, because when I go back and I speak to people there, which I do, particularly from the town that I'm from, which is a small town, I look at the math syllabus, and the math syllabus is very good. And the programming, I think, is lacking in some schools, but I think at least in the bigger cities, from what I see, programming is also becoming a big part of their studies, which is great. Is great. So I think coming forward, those two things will be well taught in school. I think we all go into physics, at least that's my opinion, because we are really curious about the world.
Right.
And what I'd say is just make sure we can, when you're in university or when you're doing research, is that you can maintain that curiosity and that enthusiasm, because it's very hard to lose it.
Yeah.
Sorry, it's very easy to lose it. Yeah. Not hard. Because when things get really difficult, when you're solving problems that are really hard, when you're solving really long equations, it can either get boring, too difficult, and so on. It's very easy to sort of let go. But I think the key thing is to keep the big problems in mind and just make sure you're driven by your curiosity. That's the only thing I would say. I think if you are driven by that, then you would do really well in general anyway, because you like what you're doing.
Right.
So if you can maintain that, then I think you're in good stead. But how do you do that? I don't know. Everybody's different, right?
Everybody has to find a way. Is there a website, some kind of a tool, something that allows somebody to go beyond what they're actually doing in a college or a school curriculum that you are aware of, or you would suggest?
Yes. So in terms of math and programming, there are certainly many, many courses that one could do online. So there are websites like Coursera and Udemy and so on that I recommend anybody to do in high school. There are so many courses that teach you how to program, and maths less so, but even math ones. So I think if you really want to pursue those, definitely do those. Those courses, they are very good and they're a lot of fun. If you want to expand just general reading and general understanding, here in the UK at least, there's a magazine that I used to read. I don't read it as much nowadays, which is a shame. Which is called Focus. It's by BBC. It's BBC Focus. That one used to be really good, that I used to like. It used to have general articles about scientific things. In India, I'm sure there are similar, but I wouldn't have them off the top of my head.
I think we have. It's available online now as well. You get Science News and Science Daily, like you said.
That's right.
Yes, Focus has as well. I've seen that as well. And of course, because of the internet available now, so people are able to access this information, and hopefully a lot of people who have heard us talking today, or students just listening to us, and especially you and all the enthusiasm, the energy that you have to speak about all this. I'm sure you're a great inspiration for a lot of people here, Dash. And what are you going to do next? What is your plan, and where are you going from here?
Well, again, thanks for being too kind with your description.
No, I'm being honest.
Well, let's hope so. Anyway, let's hope that's the end result of this. But in terms of what I'm doing next, so as I mentioned, I have a very broad overview of things that I like. So even within physics, I worked on a lot of things. But now, so I finished my PhD fairly recently, and I've moved into a slightly different field now, which is in biotech. So I'm going to be working in a biotech company. It's still in Oxford, but what we do there is we are looking to learn what we can as quickly as we can from images of tissues and cells. So I'll be doing a lot of machine learning and AI to basically look for diagnostics of diseases and tracking particles within the bloodstream and so on. So you see, it's a very different field. But the interesting thing is, as I mentioned, is the skills that you develop as a physicist, which are, being good at maths, being good at programming, And there's a lot of interesting biophysics that happens in the body as well. You can move around within fields, and that's something that I feel is perhaps not well appreciated in many areas of the world. That the nature of work is becoming very interdisciplinary, and it's very common that people move around within different fields. At least if you're interested and you're good, you can always jump around and follow your interests. So this is what I'm going to be pursuing for the next little while, at least. But again, I think it's a good example to show that you should, if you keep your horizons broad and you'll have broad interests and you work hard, you can work on different things, and it's fairly easy to do that.
And where do people find you if they want to find you? Do you have a website or anywhere where they can read a little bit more about you, your research papers, what you've done?
Sure. I mean, I used to have a website. I don't anymore. In terms of my research papers, the good thing is now research, at least in our field, is almost entirely freely available to anybody. There's a website known as Archive, which I can send a link to, in which you can read not just my papers, anybody's papers, for free. I mean, there are technical papers, so they might not be immediately accessible, but those exist. And other than that, I think I still have a web page on my university profile on the Oxford University website, which again I'd be happy to send a link to, and that has my email as well. So I'm most easily reached by that.
Great. So you said archive. So if people or kids are currently doing what they're doing, they could use that website for their research as well, right?
They could. It's not, as I say, it's a repository of research papers. So of course you can look at it. It'll be immediately accessible. It's not clear because it's research papers, right? They're quite technical. But it's always fun to just read a couple and just see what it's like, right?
Yeah, no, definitely. I think that gives you a little bit of understanding on. I mean, having an idea is one thing, but like it's always said, the three very important things that are needed for any idea, or two important things. One is timing, and the other one is rhetoric as well. So I think you've got to be able to put your idea at the right time with the right rhetoric across, and I think that gives it a framework. And the moment you can understand how a paper is published, you kind of have a framework in mind after that. And you can't have your ideas go absolutely crazy as well. You've got to keep them in control.
Of course, and if you have ideas that you do let go crazy, they just won't get published. So it's a good. I think definitely it's worth doing just to get a feel of what a research paper is like, what academic research is like, right? It's very rare that you can make very definitive statements. It's all about here's how we interpret this. This is probably what it is, and so on. So it's actually dealing with uncertainty is probably the thing that will come across most, and actually I think is the most important thing anyway, is how you understand uncertainty and have a way of appreciating your ignorance, which is really what science is about. It's about understanding your ignorance more than anything else. I can't remember there's a famous quote from someone, which is like, the most common phrase a scientist says is, I don't know. And that's so true.
Yeah, I mean, that takes a lot of intellect to say that, and humility as well, right?
Absolutely. I mean, science teaches you to do that because, as soon as you start getting into it, you realize how little we actually know. But still, I mean, it's still pretty amazing, right? That the things we discussed, that even given how little we know, we can describe the universe back to fractions of a second after the Big Bang, even though we don't see it, and so on.
Oh, that's absolutely stunning. And Dash, I've had a great time, and I know I kept you locked into the first 3 minutes or that particular phase of the Big Bang, but I think I was doing it for a reason. I think people would want to take it in bits at the moment. And thank you so much for your time and sparing your time from all the research that you're doing. And you're a busy guy, I understand, but we would love to have you back on again, and I hope you can make time for us. We could probably in future break this down into different phases, because I do understand putting it all into one hour episode can be heavy. So we may want to do this again and then break it down into just talking about, like we did the first 3 minutes, maybe we can take it from there and do a little bit more about that. But I hope you enjoyed your time with us as well, and I'm happy you kept your patience.
No, come on, thank you. It's been such a pleasure for me as well, Joachim, and I'd be very happy to be back on. And as I say, if I visit India, I'll be more than happy to come by and we can work on something together. That'll be fantastic. So yeah, I'm really happy that we got to do this, and that you took the time as well.
I'm hoping that even if one kid listens to it and then makes up his or her mind to pursue a field that we are speaking about, or just opens up and gives them some ideas, then I think this whole exercise is absolutely worth it. And especially for you as well. Having you on this podcast for a lot of us, we are all proud of you, Dash.
That's very kind of you. But as you say, yes, if only a few people listen to this and start thinking about things in a scientific way, then I think it's been a thoroughly worthwhile and enjoyable, at least for us, time.
Great, Dash. So till we talk again, all the best in your new venture, in whatever you do into the biotech field, and maybe the next time we talk, we'll talk a little biotech.
Sure, that sounds great, Joachim.
Thanks, Dash.
All right. Thanks a lot.
Thank you.